This is pre-calc's video for section 1.15, and instead of me stumbling through my words, I'm just going to share the answer key with you. That way I'm giving you exact definitions and exact rules for one-to-one functions. So as a reminder, and we should understand this already, this first definition, that a function is any relationship, so sometimes we call it just a relation, between x and y values so that x never repeats. And that's where we get this, this statement where the x value only corresponds with one y value. So in other words, the x value does not repeat. So as you look at that first part where it says if the point 2, -3 is a graph of a function, then there's no other point that can have an x value of 2. Because if there is, then the x is repeating and it's no longer a function. So feel free to pause the video and write down anything you want to from that first statement. So what we're going to explore today is a one-to-one function. And with a one-to-one function, it first of all has to be a function, so the x value cannot repeat. And in order to be one-to-one, that means that there's exactly one y value for each x value. In other words, y values can no longer repeat. So a function can have y values repeat, and it's fine. A one-to-one function cannot have y values repeat. It also cannot have x values repeat. So feel free to pause the video and write down anything else you want before I scroll down to the numerical determination. So you've probably figured out by now that I'm all about the 3 different ways of learning math, and you're used to the analytical equations that we give you, and you can use a graphing calculator to figure out if a function's one-to-one, and I'll get more into that when we get to the inverse. But before that is the numerical. Numerical means that you're looking at a table of x and y values. Now there's 2 different types of numerical determinations. A discrete one is just a list of ordered pairs. Now if it's discrete, it's just saying that you're jumping from one point to the next. There's no connecting dots. So if you're looking at a discrete, it just means the y values cannot repeat. We're assuming that it's already a function, so the x values already do not repeat. Now if it's continuous, you want to double check that it doesn't change from increasing to decreasing or decreasing to increasing. So that's where we get this phrase where if it's continuous, the function needs to either always increase or always decrease. And we have an example to look at when I actually start writing for you. The graphical determination is really, really easy. And the reason why I say that is you're already used to the vertical line test. Well, the vertical line test is to see if any of the x values repeat. So this time, if we want to see if the y values repeat, we look at the horizontal line test, and we shorten it as HLT. And by the way, we write it this way of 1, 2, 1. And sometimes I write it slightly different because I've had it in the past where I write 1, 2, 1 like this. And students are like, why'd you write 1 minus 1 right there? Or why'd you write the absolute value of the negative sign? So sometimes I write it a little bit different than 1, 2, 1, but this is accepted way of writing it. So again, graphical is passing the horizontal line test. So I'm going to stop right here, let you pause and write down anything you want before I scroll down to talk about the inverse. By the way, if you look at the graph of an analytical with a graphing calculator, whether you use Desmos or an actual graphing calculator, you can see if it passes the horizontal line test that way. So as I scroll down to talk about the inverse, what the inverse is, I'm confident you learned this in Algebra 2, is it's when you switch the x and y values. In other words, the domain and the range are switched of a function. So in order for a function to exist, the inverse must, I said that wrong. In order for the function to have an inverse, the function must be one-to-one. And this explains why. If the function is not one-to-one, and you switch the domain and range around, well, then you fail the vertical line test. So if you fail the vertical line test, then that inverse would not exist. So in order for you to have an inverse that exists, the function must pass both the vertical line test and the horizontal line test. I feel like I've over-explained myself right now, so again, just pause the video, read this, soak it in, and get back to me either through email or in class if you are struggling with this premise. And I will get into examples, so stick with me. So how do we find the inverse? Well, numerically, remember that's with a table. All you have to do is switch the x and y values. That is it. Now, as far as being continuous or not, or discrete, well, if it's discrete, just switch them. Not a big deal. But if it's continuous, you would have to connect the dots in that same order. And I hope that makes sense. Because in a continuous function, you connect the dots. With a graph, you switch the x and y, and just like what I said before, connect the dots in the same way. And then analytically, this is probably what you remember from Algebra 2, is you switch x and y in the equation. Then you solve the new equation for y, and in pre-calculus we usually write everything in function notation, which is the symbol that looks like f to the -1 power. That's actually your symbol for inverse, and that's why on your calculator, when that key that looks like to the -1 power, that's actually called the inverse key. So again, I'm going to pause the video, and then I'm going to go back to, so I can actually write in my slides. There we go. So in this problem, we're going to look at x and f of x. All right. So I think all it asks you for is to determine if the inverse exists or not. Well, if the inverse exists, then it must be one-to-one. So first of all, double check that this is a function. I believe I give you only functions. But do any x values repeat? No. So this is a function. We are good to move forward. Before checking if what the inverse is, double check if it's one-to-one. So do any y values repeat? Well, since the 2 repeats, since f of x equals 2 has 2 different x values, in other words, the y value repeats. F of x is not one-to-one. And this is how I write it. Sometimes I'll actually write it out with 1, 2, 1. Sometimes you'll see me write it like this: 1, 2, 1. It's very rare that I actually write 1-1. But anyway, what that means is the inverse of f does not exist. I'll just write DNE for does not exist. All right. As we look at the next function, and again, I'm going to assume this is discrete. It's just a set of ordered pairs for right now. It is a function. None of the x values repeat. And if you look at this, none of the y values repeat. So is this inverse exist? Yes. I'm going to assume it's discrete for right now. It is 1, 2, 1. So the inverse exists. And I believe we're supposed to give what the inverse would be. I'm just going to write it as a table just like this. And then our notation would be f to the -1. This means the inverse of f. And you switch your x and y coordinates around. So 6 becomes an x coordinate. -2 becomes an x coordinate. There we go. Now what if this function were continuous? Well, now if it's continuous, the inverse would not exist. Why? Well, if you look at this graph and you were to just plot a few points, you could actually stop once you get from -1, 6 and 1, -2 and 5, -1. And while I'm at it, I might as well put 3, 2 and 2, 3 on here. And let's say we just connected these dots, so it was a function, so it passed the vertical line test. Well, if you notice, by connecting these dots, we have multiple y values that are hitting the same points. And you can see my vertical lines there. So if this function were continuous, it's not only decreasing, it changes from decreasing to increasing to decreasing again. So by changing increasing to decreasing, it fails the it fails the horizontal line test. And that's why we have this rule that you have to pay attention to the directions if it says it's discrete or continuous. And if there's ever confusion, please reach out to me and let me know, like, hey, is this supposed to be discrete or continuous? And move on. So this is another problem where now we're looking at a graph of f of x. Now, if you just look at this graph, I think you could quickly say, okay, well, it definitely passes the vertical line test. Now your new test is, does it pass the horizontal line test? And this answer is yes. So an inverse exists. Now what I'm going to ask you to do is write down both ordered pairs for right now, and I think the directions are pretty clear in the future. So as you look at your ordered pairs of -5, 5, and then -2, 1, let's see, 2, -1, and then 4, -4. Well, if I asked you for the inverse and what that function would be, you have to switch. So the x-coordinate, -5, becomes the y-coordinate. And what was the y-coordinate becomes the x-coordinate. So this ordered pair would be at 5, -5. Then this one would be 1, -2. Let's see, -1, 2. And then -4, 4. Sorry, it kind of got messy there. But we could connect those dots. And what you would notice, and this is true of all inverses, is this also passes the vertical and horizontal line test. And I'm going to take it one step further because I think you guys are smart enough to figure this out. Is these are actually a y equals x reflection. So the reflection over the diagonal line y equals x. And quickly doing part D, yes, this is a function, but I'll just pick a quick horizontal line in here. Crosses more than once, so it fails the horizontal line test, and therefore the inverse of g does not exist. Alright, so I'm at my time limit for this, and I believe we have some more notes to take before you're ready for the homework. So pause the video before moving on.